Okay, so we're going to talk about some driving forces for reactions. Why do some reactions happen and others don't? For example, if you have an iron nail sitting outside in the rain, it's going to rust. It's going to change from iron into something called rust, and rust is iron 3 oxide. It's going to happen. But if you put rust outside, it never turns back into iron. And so we're going to talk about one of the driving forces for reactions, why things happen. So this can tell you whether or not a reaction is going to happen. Chemical changes that tend to make the reactions go in the direction of the arrow. In other words, iron will turn into rust, but rust will not turn into iron. So driving forces are what force a reaction to proceed based on our observations. If none of the driving forces are present, the reaction should not occur. So there are 4 types of driving forces. 1, if you form a precipitate, that's another word for a solid in a double replacement reaction. So double replacement, we're looking to form an S. Okay? So, for example, silver nitrate, potassium chloride, it's compound and a compound, drop and swap, predict the products, and one of them is a solid. And so therefore you know that that reaction will happen. We did that in one of our dropper labs. If it forms water in an acid-base reaction, so acid-base will form water, which is actually a liquid. So we're going to use that one as one of our backups. So HCl, NaOH forms liquid water, and that should say NaCl. I don't know why that says NaOH. That's a typo. Formation of a gas in a combustion or decomposition reaction. This is another driving force, forming a gas. So combustion, it forms CO2. And very often it produces so much heat that it produces water, and the water instantly boils. Okay, so that's a good example of it. Okay, so another example is a decomposition. This is what happens in soda. It produces carbon dioxide. And then this last one, single replacement, electrons get transferred in a single replacement or a synthesis reaction. They transfer electrons. So synthesis as well. So this one and this one, they transfer electrons and they end up forming compounds. Or in a single replacement, these guys end up trading electrons and they form products. So we're going to use classifications, which we learned about earlier, to determine the products. So first of all, determine the type of reaction you're dealing with based on the reactants given. Predict the products based on the type of reaction. And then for most of the reactions, not all, most of them you're going to drop and swap to figure out the products, formulas. Remember, the metals are always written first. The positive ions are always written first. And then balance using the coefficients. Now, I know people want to jump into this and balance and balance and balance because it's easy and you're good at it. Okay? Be patient. Focus on that a lot. Because if you screw up the formula of the products, you may never be able to balance. It may be impossible to balance. So that's really important to focus on the formulas. So we're going to start with just this one, forming a precipitate. So this is double replacement, forming something that is a solid. So most double replacement reactions take place in aqueous solution. That means it's dissolved in water. And aqueous ionic compounds will dissociate in solution. They'll form a bunch of different ions. And what you'll see is if they form a solid, then that's considered to be a reaction. So dissociation means they break apart into their ions. So really, there's no such thing as NaCl with the aqueous afterwards. It actually exists as Na plus and Cl minus, and they're all floating around in water. Ammonium acetate exists as ammonium and acetate. You break it apart into its name. That's how they break apart. And what happens is when they trade places in a double replacement reaction, one of the products has to form a solid or there is no reaction. So how do we know which one is a solid? Well, good question, because we need to know that. We're going to use something called the solubility rules. And the solubility rules determine which substances will stay dissolved and which one will become a solid. If you look on the back of your periodic table, that's where it is for Mrs. Packard and Mr. Lindenberger. I think Miss Ellis has it in her resources packet. So here's the rules. Anything with NO3 is always aqueous, never solid. Anything with acetate is always aqueous, never solid. Anything with the alkali metal compounds, so any of these guys including hydrogen and anything with ammonium, are always aqueous. So these are not ever solids if it's got one of those in it. Okay. Now, once we get to the halides are column 17, halogens. 1, 2, 3, 4. Those four. Fluoride, chloride, bromide, and iodide. Now, they are mostly aqueous. Some that are not are AgCl solid. That would also apply to AgI, AgF, and AgBr. Same thing with the Pb. PbF, PbBr, and PbI2. And the same thing with mercury, although we won't do much with mercury. But if you replace any of these guys in one of these, they are solids. Okay, so that's our solid and solid and solid. But we won't do much with mercury. I don't like playing with mercury. Okay, the next rule is most sulfates, things that have sulfate in them, are aqueous. The ones that are exceptions to the rule are barium, lead, calcium, and then slightly soluble is AgSO4. This is slightly soluble. So if you would want to call it solid, I would be okay with that. Ag2SO4, sorry. So these guys are the solid ones. And then most hydroxides are not soluble, meaning they are solids. So CaOH2 is a solid, or AlOH3 is a solid. The ones that are not solids, the ones that are aqueous, are the ones that fall under our first rule of alkali metals. The rule about alkali metals up here, if it's got an Li, an Na, or a K, then that rule is overriding on this one. So those guys are all aqueous. Anything else is pretty much going to be a solid. And then the last rule, everything else is pretty much a solid, if it doesn't fall under one of these rules up there. So, predict the products of the following double replacement reactions, if there are any, and determine which product is a solid using the solubility rules. So, here it is. I have a double replacement reaction, and in double replacement, here's the way it works. The Na and the Ba are going to trade places in order to figure out what the product is for the from the reactants. You're going to put the Na with the NO3, and I'm just going to write them down next to each other like this, and I'm going to write the Ba next to the OH like this, but you must drop and swap. So if you look up the charge on Na, it's a +1, and you look up the charge on NO3, it's -1. So when I drop and swap, I get NaNO3. And here, barium is +2, according to the periodic table. Hydroxide is -1. When I drop and swap, I get BaOH2. So I'm going to erase the ink on here so y'all can see how this works. So the idea is the Na and the Ba trade, and I came up with the formulas. NaNO3 and BaOH2. One of those two has to be a solid. And so what you want to do is look back at our rules, where our very first rule said anything with NO3 in it is automatically aqueous. Okay, so it's automatically aqueous. So now we're looking at barium hydroxide. And the second to last rule, the rule about hydroxides, says that anything with hydroxide other than the alkali metals is a solid. So there's my reaction. Then I need to balance it. So I'm not even close to being done yet. I have 1 Ba, 2 of the NO3s, and I have only 1 of the NO3s, so I'm going to put a 2 there. And I have 1 Na, and I have 2 Na, so I need to put a 2 here. And I have 2 of the hydroxides and 2 of the hydroxides. So now it is officially, completely 100% done. Okay, so again, double replacement. I got 2 compounds, so the Fe and the Ca are going to trade places. Now I want you to notice one thing. I'm not taking that 2 with me. Okay, that 2 was dropped and swapped and actually belongs to that sulfate. I should say that sulfate. Okay? What that means is this 3 that was dropped and swapped actually belonged to the Fe. So that's what I'm going to take with me as the charge. So when I switch them, I'm going to have Ca with SO4, and I'm going to have the Fe with the acetate. Okay? And now I need to drop and swap for the products. So calcium is positive 2, sulfate is negative 2, drop and swap, you get CaSO4, plus, like I said, that 3, remember when we did Roman numerals, belonged to the Fe, just like that 2 belonged to the sulfate. So it has a 3 charge, acetate has negative 1, so when I drop and swap, I get this. Okay, so not using this anymore. And so I need to figure out which one of these is a solid. So I'm going to look at my rules, and one of my first 2 rules says that anything with acetate is automatically aqueous. So I need to look at this one. Okay, there's no rules for calcium, but if you look at the rule for sulfate, it does say there are some exceptions, and this is one of the exceptions. It is a solid. Okay, so go ahead and take a couple of minutes. Let's go through these. Again, what you're going to do is you're going to take the K and you're going to switch it with the first thing. In this case, it's going to be NH4. The positive ions trade places. Here it's going to be Pb and Al, K and Na. They're going to trade places. Not the numbers that go with them, just the formulas. Now, NH4 does keep its 4 because remember that's ammonium. And it's that 4 belongs to it inside the parentheses. Okay, so when I switch the cations, I have K with Cl, and I have that NH4 with ClO3. Okay, drop and swap charges, 1 plus, 1 minus, 1 plus, 1 minus, so it's all good. Now you have to figure out which one of these is a solid. Now according to my, I think it's the 3rd rule, it talks about the halides. Anything with Cl in it is going to be aqueous except lead and silver. So this one is aqueous. And then one of my first 2 rules says anything with ammonium is automatically aqueous. So in this case you would write no reaction because nothing formed a solid. You've got to form a solid for there to be a reaction. So let me contrast that one with this one. The Al is going to trade with the Pb. I'm going to have the Al with the NO3, and I have the Pb with the Cl. Now I need to figure out the charges and drop and swap. Al is positive 3 off the periodic table. NO3 is 1 minus, not 1 plus. And then I need to figure out what Pb's charge is. Well, I just said nitrate is negative 1. That means this 2, to undrop and swap it, came from the lead. So it's positive 2 and chloride's negative 1. So when you drop and swap, you end up with Al, NO3, 3. So that 3 moves here. And PbCl2. So once I've dropped and swapped, I need to figure out which one of these is solid. First rule, anything with nitrate is automatically aqueous. 3rd rule, I think it is the halides. Most halides are aqueous except Pb and silver. Okay, so now I have my solid. To balance this one, I have 1 Pb and 1 Pb. I have 2 of the nitrates. I have 3 of the nitrates, so I'm going to put a 2 here and a 3 there. That gives me 3 Pbs, 6 Cls. So I need to put a 2 here and 2 Als and 2 Als. Okay, but the last thing you do is balance. You do everything else first, and you spend some time on it. Do not rush formulas, because if you rush the formula, you will never be able to balance it. Okay, here I'm going to have the K switch with the CO3, and I'm just writing in the charges because I already know what they are, and the Na with the NO3. When I drop and swap, I get K2CO3 and NaNO3. And again, you have to figure out if one is a solid. Well, one of my first rules says anything with nitrate is automatically aqueous. Also, in the 2nd rule, anything with sodium and potassium is automatically aqueous. Therefore, this is no reaction. Don't need to balance it if there's no reaction.